Hello all. Today we will discuss a topic in discrete mathematical structures. 18 CS 36 is the subject code for the same. I'll be discussing a topic in module 3, relations and functions. And the topic name is relations, matrix, digraph, and composition of relations. So we will be looking into matrix of a relation, digraph of a relation, and composition of relations. Myself, Dr. Madhura, Assistant Professor, Department of Mathematics, Sai Vidya Institute of Technology, Bengaluru. First, let us see the definition for relations. Let A and B be two relations, two sets. Then a subset of A cross B is called a binary relation or just a relation from A to B. We are considering two sets A and B. A cross B is a set of all ordered pairs A comma B such that A belongs to A, the set A, and the element B belongs to the set B. We discussed that in the Cartesian product of sets. So the subset of A cross B is called a binary relation or just a relation from A to B. Suppose R is a relation from A to B, then R is a set of ordered pairs A comma B where A belongs to the set A and the element B belongs to set B. Or conversely, if R is a set of ordered pairs A comma B, where A belongs to the set A and B belongs to set B, then R is called the relation from A to B. So collecting all the set of ordered pairs A comma B such that R is related to A and B. So if A comma B belongs to R, we say that A is related to B by R. The element A is related to B by the relation R and it is denoted by A is related to B. A, R, B. We read this as A is related to B. If R is relation from A to A, that is R is a subset of A cross A, then we say that R is a binary relation on A. So suppose we have taken only the set A and R is a relation from A to A itself, then R is a subset of A cross A, then R is a binary relation on the set A. Example, suppose we take the set A as 0, 1, 2 and the set B as 3, 4, 5. Let us assume the relation R as 1, 3, 2, 4, 2, 5, where R is a subset of A cross B. So if I want to write down the Cartesian product of A cross B, it is set of all those elements, ordered pairs A comma B. So it will be 0, 3, 0, 4, 0, 5, 1, 3, 1, 4, 1, 5. Similarly, 2, 3, 2, 4, 2, 5. That will be A cross B. So among that, I have collected a subset which is nothing but the R, which is given by 1, 3, 2, 4, 2, 5. This is represented by the diagram as shown below, which is called as arrow diagram. So the relation R can be represented as in the form of a arrow diagram. So I have the set A and the set B. R is the relation from A to B. So 1, 3 is related. So 1 to 3, we have an arrow. 2, 4 is related. So 2 to 4, there is an arrow. 2, 5 is related. So 2 to 5, there is an arrow. So this is a simple example of a relation that I considered. Next, we'll note this point. If A has m elements, if A has m elements and B has n elements, then the number of relations from A to B are 2 power m into n. So you have considered A carrying m elements and B carrying n elements. So we are finding the total number of relations. So total number of relations from A to B will be 2 power m into n. 2 power m into n. Next, we'll learn about matrix of a relation. Consider the sets A equal to A1, A2, A3, etc. up to Am. There are m elements in the set A. Consider another set B, which is B1, B2, B3, etc. up to Bn. There are n elements in the set B. That is why we have written here orders as m and n respectively. Then the set A cross B contains all the ordered pairs of the form AI, Bj, where I lies between 1 to m and j lies between 1 to n, which are totally m into n in number, means A cross B consists of totally m into n elements. Let R be a relation from A to B so that R is a subset of A cross B. Let Mij represent the matrix representation. We give the value as 1 if Ai is related to Bj. We give the value as 0 if Ai is not related to Bj. The same thing is represented in another representation, that is Ai Bj belongs to the relation R and Ai Bj does not belong to the relation R. Then the m cross n matrix formed by Mij is called the relation matrix for R or the adjacency matrix of adjacency matrix. Alternately, it is also known as 0-1 matrix for R. 0-1 matrix for R. It is usually denoted by M of R matrix R or M suffix R. M suffix R. So here we are trying to understand how to write down the matrix of a relation. So we say that if AI is related to Bj, we write down in the particular row as 1 if AI is related to Bj. In the same manner, if AI is not related to Bj, we write the element as 0. So that we can predict from the relation defined for us from A to B. From A to B. So here the relation R is always a subset of Cartesian product of A and B. That is A cross B. So such a representation, matrix representation is called as the relation matrix for R or adjacency matrix, also known as 0-1 matrix. 0-1 matrix. Moving further, rows of MR corresponds to elements of A and columns corresponds to elements of B. So usually when we write down the matrix relation, we represent the rows as the elements of A and usually we represent the columns by the elements of B. When B is equal to A, the set B, if it is equal to the set A, then MR, that is matrix relation, is an n cross n matrix whose elements are Mij is equal to 1 if AI is related to Aj, otherwise 0. Means if AI is not related to Aj, we write down the element as 0 in the matrix. So this happens when the set B is equal to A itself. Let us take down an example. Suppose A equal to 1, 2, 3, 4, B equal to 4, 5, and the relation R is equal to 1, 4, 2, 5. So I have taken two sets. I am trying to write down the matrix relation from A to B. So A is taken as the elements 1, 2, 3, 4 and the set B is taken 4, 5. Relation R is defined for us as with the ordered pairs 1, 4, 2, 5. Then the matrix relation can be represented as, we take, as mentioned, we take along the rows we take 1, 2, 3, 4. That is elements of set A. And along columns we take elements of set B. Here the elements of set B are 4 and 5. Then the matrix relation is of this form. Let us understand how it is. The relation R is 1, 4. So 1 is related to 4. 1 is taken from the set A, 4 is taken from the set B. Because this is a relation from A to B. So 1, 4 represents, so 1 belongs to the set A and 4 belongs to the set B. So 1, 4 is related to each other. 1 is related to 4. So we assign a 1 there. 1 is not related to 5. So we assign 0. Means 1, 5 does not belong to the relation R. That's why it is assigned 0. Similarly, 2, 4. 2 is not related to 4. 2, 4 does not belong to the relation R. So 2 is not related to 4. That's why we assign 0. 2 is related to 5 because R has the set 2, 5. So 2 is related to 5. That's why we assign 1. So if any AI, Bj belong to the relation R, then we assign 1 in that place. If AI, Bj does not belong to the relation R, then we assign 0 in that place. So this is a simple example to understand the matrix relation. Now we understand digraph of a relation. Let R be a relation on a finite set A. To get the digraph of R, we follow the following procedure. We are assuming R is a relation on a finite set A and we try to draw the digraph of the relation R with the following procedure. Procedure is step 1. We draw a small circle or a bullet for each of the elements of A and label it. These circles are called vertices or nodes. Secondly, we draw an arrow called an edge from a vertex X to a vertex Y if and only if X, Y belongs to R. Means if X is related to Y, then we draw an edge from X to Y. If Y is related to X, if suppose Y is related to X, then we draw an edge from Y to X. This in the form of an arrow we are going to represent the edge. So firstly, we draw a small circle or in the form of a bullet which represents the elements of A and we label it. And the circles or the bullets that we draw represents the vertices or the nodes. And we draw an edge in the form of an arrow from a vertex X to a vertex Y if and only if X is related to Y. X is related to Y. In a digraph, a vertex from which an edge leaves is called the origin or the source for that edge, and a vertex where an edge ends is called the terminus for that edge. So any particular vertex is called as an origin or the source if an edge leaves from it. Similarly, any other vertex is called as a terminus if an edge ends at that vertex. So these are definitions for origin and terminus. Next, a vertex which is neither a source nor a terminus is called as an isolated vertex. Suppose no edge is coming to that vertex or no edge is left from a particular vertex, then it becomes obviously an isolated vertex. Next, about loop we are trying to understand. An edge for which the source and terminus are the same is called a loop. Suppose we draw an edge from a particular vertex onto the same vertex we end. The source and the terminus are the same. The initial and the end vertex are the same. Then such an edge is called a loop. The number of edges terminating at a vertex is called the in degree of that vertex. So we can find out the in degrees and the out degrees for any vertex by the following definition. The number of edges terminating at a vertex. At a particular vertex, we look into how many number of edges are terminating, means ending, is called the in degree of that vertex. Then out degree means the number of edges leaving a vertex. Starting from a vertex, how many number of edges are left leaving a vertex is called the out degree of that vertex. So these are some of the definitions which we have to understand in digraph of a relation. So how to draw a digraph, and then how to recognize the loop and find out the in degrees and the out degrees of the vertices. Let us take a simple example to understand how to draw a digraph. Let us consider set A equal to A, B, C, D. There are 4 elements in the set A. And R be a relation A on A. We are defining a relation A on A itself, which is given by, suppose, R equal to A comma B, B comma B, B comma D, C comma B, C comma D, D comma A, and D comma C. This is a given relation for us. We are trying to now draw the digraph for the same. So let us understand how we are drawing this digraph. So I have considered each of the elements in the set A as the vertices or a circle. So I have here considered a circle and drawn the 4 vertices of the set A. A, B, C, D. A, B, C, D. Represented in the form of circles here and named. Now there is an arrow or an edge from A to B. So A comma B represents A is related to B, it says. So that's why we are drawing an edge from A to B. B comma B represents a loop. We are starting from the vertex B and ending at the vertex B. So from B to B, we have drawn a loop here. B comma D. So B is related to D. So draw an edge from B to D. Arrows are important here. C comma B. So from C, there is an edge to B, or C is related to B. So C to B, we are drawing an edge. C comma D, C to D. D comma A. So D to A, there is an arrow because D is related to A. D comma C. So finally, D comma C is also drawn. So this is a simple example to understand how we draw the digraph from the procedure what we saw. Next, operations on relations. Operations on relations. Union and intersection of relations are the operations that we learn here. Given the relations R1 and R2 from a set A to a set B, the union of R1 and R2, usually denoted by R1 union R2, is defined as a relation from A to B with the property that A comma B belongs to R1 union R2 if and only if A comma B belongs to R1 or A comma B belongs to R2. So suppose I have two sets A1, R1 and R2. They are the two relations from a set A to a set B being defined for us. Then we can obtain the union of those relations R1 and R2, usually denoted by R1 union R2, with the property that A comma B belongs to R1 union R2 if and only if AB belongs to R1 or AB belongs to R2. Either of these two it has to. The ordered pair A comma B should belong to either R1 or R2. Then the union can be obtained. The intersection of R1 and R2 denoted by R1 intersection R2 is defined as a relation from A to B with the property that A comma B belongs to R1 intersection R2 if and only if the ordered pair belongs to both R1 and R2. The ordered pair A comma B belongs to R1 and A comma B belongs to R2. So it is intersection of two relations R1 and R2. Next, we understand the definition for complement of a relation. Given a relation R from a set A to a set B, the complement of R denoted by R bar or R complement, we read it as, is defined as a relation from A to B with the property that A comma B belongs to R complement if and only if the ordered pair A comma B does not belong to R. So we say, how do we find out the complement of a relation is, any ordered pair A comma B belongs to R means then the ordered pair A comma B does not belong to its complement. So it is vice versa also true. If A comma B belong to the R complement, then A comma B does not belong to the relation R. Here R is a relation from the set A to the set B. In other words, R complement is the complement of the set R in the universal set A cross B. Means, suppose we want to obtain R complement, that is A cross B minus of the relation R. A cross B is nothing but the set of all ordered pairs A comma B, where the element A belongs to the set A and B belongs to the set B. So it's nothing but the universal set, we can say. So A cross B minus of the relation R, whatever the elements that are there in the ordered pairs that are there in the relation R. So if you subtract from the universal set, we get R complement. Next, we'll understand converse of a relation. Converse and complement are different. Do not get confused between them. Converse of a relation means, given a relation R from a set A to a set B, the converse of R denoted by R superfix C, C in the superfix represents the converse, so RC, we read it as, is defined as a relation from B to A with the property that A comma B belongs to R converse if and only if B comma A belongs to R. So suppose I have the ordered pair A comma B existing in the relation R, then B comma A exists in the R converse. So given any relation from set A to set B, I'll be able to find out the converse of a relation from B to A if it is satisfying this property that if AB belongs to R, then BA belongs to its converse. Vice versa is also true. That is, AB belongs to R converse if and only if B comma A belongs to the relation R. Next, we note this point. If MR is the matrix of R, then MRT is the matrix of R converse and R converse, the whole converse is equal to R. MRT stands for transpose of a matrix of a relation. So if at all we know we are able to write down the matrix of a relation R, which is given by MR, then the transpose of the matrix of the relation is the matrix of R converse. And hence we can write it down. R converse, the whole converse is equal to R itself. Now composition of relations. Consider a relation R from a set A to a set B and a relation S from a set B to a set C. So we are trying to consider two relations R and S. R is defined from A to B and S is defined from B to C. Then the product or the composition of R and S is a relation from the set A to the set C denoted by R composition S. This is the symbol, a small circle is a symbol for composition. So I'll repeat the definition for you. So we have considered two relations R and S. R is defined from A to B and S is defined from B to C. The product or the composition of R, we are considering the product, or it is also called as a composition of R and S. It is also a relation. So it is relation from A to C, usually denoted by R composition S. And it is defined as if if A belongs to the set A and C belongs to set C, then A comma C belongs to R composition S if and only if there is some B belonging to set B such that A comma B belongs to R and B comma C belongs to S. That is, R composition S is equal to R composition S is equal to set of all ordered pairs A comma C such that A belongs to the set A, C belongs to the set C, and there exists a B belonging to the set B with A comma B belongs to the set relation R and B comma C belongs to the relation S. So this is R composition S for us. We can understand the composition of two relations better well when we take up examples on the same. So I'll just note these points for better understanding. R is a subset of A cross B. S is a subset of B cross C. Then R composition S is a subset of A cross C. Whenever we take cross product of any two sets, it is a set of all the ordered pairs that are there in those two sets. So the relation R will be obviously a subset of A cross B. S will be a subset of B cross C. And R composition S will be a subset of A cross C. Nextly, R composition S is never equal to S composition R. This we can relate to our product of the matrices kind of. A into B is never equal to B into A. No, in that manner we can understand this also. Because here also we will be doing the product, which in turn nothing but the composition of two relations. Thirdly, if R is a relation on A, then R composition R is a relation on A denoted by R square. So if I don't consider two relations R and S, then if I simply consider a relation R only, which is a relation on A itself, then R composition R is a relation on A denoted by R square. It becomes like a usual multiplication R into R, which is R square. And R composition R is also a relation on A, usually denoted by R cube. So even this becomes, it's a product of R 3 times. So R into R gives us R cube. If this can happen only when R is a relation on A itself. Next, let R be a relation from A to B and S be a relation from B to C. Then the matrices of R, S and R composition S satisfy the property matrix R into matrix S is equal to matrix of R composition S. So suppose we have considered two relations R and S, where R is a relation from A to B and S is a relation from B to C. Then I can apply this property on R, S and R composition S. That is matrix R into matrix S is equal to matrix R composition S. This property holds good if we find out the matrix R and matrix S and multiply here. This will be always equal to matrix of R composition S. Next, matrix of R power n is always equal to matrix of R whole power n. This is true for all n belonging to set of all positive integers Z. Lastly, suppose A, B, C, D are the sets and R, S, T are the relations from A to B, B to C, C to D respectively. Then this property holds good or it is true always. R composition of S composition T is equal to R composition S of composition T. So it is similar to the associative property what we usually understand. So A, B, C, D are the four sets considered here and R, S, T are the three relations considered from A to B, B to C, C to D respectively. Then this is always true that R composition of S composition T is always equal to R composition S of composition T. So these are some of the important things what we understand about matrix of a relation, digraph of a relation, operations on relations, and finally on compositions of relations. Composition of relations. Now, let us see problems on relations, matrix of a relation, digraph of a relation, and composition of relation. We are doing problems. So firstly, I would like to take an important problem from simple definition of a relations and the number of relations in it. So first question, let the set A be equal to 1, 2, 3 and set B is given as 2, 4, 5. Determine the following. Determine the following. First one, cardinality of A cross B. Second one, number of relations from A to B. Number of relations from A to B. Third one, number of binary relations on A. Number of binary relations on A. Fourth one, number of relations from A to B. number of relations from A to B that contain 1, 2 and 1, 5. Fifth sub-question. Number of relations from A, B number of relations from A to B that contain exactly 5 ordered pairs. 5 ordered pairs. And the last sub-question, number of binary relations on A that contain at least 7 ordered pairs. That contain at least 7 ordered pairs. So let us see the solution one by one. Solution. From the data, it is given that cardinality of A, usually we denote this by M, is 3 because there are 3 elements 1, 2, 3 in the set A. And number of elements in B is also 3 because there are 3 elements in the set B. B, usually we denote the cardinality of B as n, and this is also equal to 3. Now the first one is number of elements in A cross B. Number of elements in A cross B is nothing but the number of elements in the Cartesian product of A and B, which is given by M into N. So 3 into 3, which is 9. Second one, number of relations from A to B. Number of relations from A to B is given by 2 power M into N. 2 power M into N, which is 2 power 9, which is equal to 512. This is number of relations from A to B. Thirdly, third sub-question is to find the number of binary relations on A. Means we are obtaining relations from A to A itself. So which is given by number of binary relations on A is 2 power M into M, which is 2 power M square or 2 power 9 itself, because M value is 3, 3 square is 9, which is also equal to 512. Fourth one, we have to find number of relations from A to B that contain these ordered pairs 1, 2 and 1, 5. See, when we do the set of all ordered pairs A cross B, we have 3 into 3, 9 elements. That is 1, 2, 1, 4, 1, 5, 2, 2, 2, 4, 2, 5, and nextly 3, 2, 3, 4, 3, 5. This is These are the ordered pairs from A to B. That is nothing but the Cartesian product of A and B. Now, we have to find out in the fourth subcase, it is number of relations from A to B that contain only these two ordered pairs. That is 1, 2 and 1, 5. So let us assume R1 equal to those ordered pairs given, that is 1, 2 and 1, 5. Every relation from A to B contains these elements 1, 2 and 1, 5, and this is of the form R1 union R2, where R2 is a subset of R1 complement in A cross B. So we are trying to find all such relations which gives us the number of subsets of R1 complement. We'll write down that first and try to understand later. So every relation from A to B, every relation from A to B that contains the elements that contains the elements 1, 2 and 1, 5 is of the form R1 union R2, where R2 is a subset of R1 complement in A cross B. So we are trying to take all those relations from A to B which contains these elements 1, 2 and 1, 5 from the union of R1 and R2, where R2 is nothing but the subset of R1 complement in A cross B. We have already denoted R1 as 1, 2 and 1, 5. Now we are taking R2 as a subset of R1 complement from A cross B. Therefore, number of such relations is equal to number of subsets of R1 complement. Now the number of subsets of R1 complement we want. So first let us find out what is the value of R1 complement. So R1 complement is given by number of elements in R1 complement is number of elements in A cross B minus number of elements in R1. Number of elements in A cross B minus number of elements in R1. So there are 9 elements in A cross B and R1 has 2 elements. R1 is a set which is 1, 2 and 1, 5. So R1 has 2 elements. So this is equal to 7. So this is the value for number of elements in R1 complement. Now number of required relations becomes, we have to consider number of subsets of R1 complement, which is nothing but 2 power 7, which is 128. Thus, we can conclude there are 128 number of relations from A to B that contain the elements 1, 2 and 1, 3. This was our fourth question. Now moving ahead to the fifth one. Fifth question. We have to find number of relations from A to B that contain exactly 5 ordered pairs. That contain exactly 5 ordered pairs. Now, we can solve this in this manner. Since A cross B contains 9 ordered pairs, the number of relations from A to B that contain exactly 5 ordered pairs is nothing but this is equal to number of ways of choosing 5 ordered pairs from 9 ordered pairs. So we are doing the selection here. So out of 9 ordered pairs, we are choosing 5 ordered pairs that contains the number of relations from A to B. So this number is equal to 9C5. Out of 9, we are selecting 5 ordered pairs. So this is 126. And finally, the sixth sub-question. Sixth one. Number of binary relations we have to find out. Number of binary relations on A that contain at least 7 ordered pairs. Number of binary relations on A that contain at least 7 elements, 7 ordered pairs is, so out of 9 we can select 7, or out of 9 we can select 8, or out of 9 we can select 9. So we have to select at least 9 ordered pairs, so 7 or 8 or 9. Some rule exists here, that is why plus in the middle, which gives us the answer as 46. 46. So this is one of the basic problem in relations. We'll take up next question. Next question I would like to consider on digraph. Second question. Let A be the set 1, 2, 3, 4, 6 and R be the relation on A. R be the relation on A defined by A is related to B if and only if A is a multiple of B. If and only if A is a multiple of B. We need to find the following. First one, represent R as a set of ordered pairs. Represent R as a set of ordered pairs. Second one, draw its digraph. Thirdly, determine the in degrees and out degrees of the vertices Fourthly, write the matrix of R. Write the matrix of the relation R. Let us see the solution. So firstly, it is given that A is the set given by 1, 2, 3, 4, 6 and R is the relation on A defined by A is related to B if and only if A is a multiple of B. So we'll just mention that and find out the relation R, which is a set of ordered pairs such that A is related to B in such a manner that A is a multiple of B. So let us find that ordered pairs relation R first. So it is given A comma B belongs to R if and only if A is a multiple of B. A is a multiple of B. So first one, the relation R is given by all such ordered pairs we have to collect relation R on A. Two elements A comma B are in such a way that A is a multiple of B. So 1 comma 1, we can say 1 is a multiple of 1. Then 2 comma 1, 2 is a multiple of 1 because I can say 1, 2s are 2. So 2 is a multiple of 1. 2 comma 2, 2 is a multiple of 2. Then we can say 3 comma 1, 3 is a multiple of 1, 3 is a multiple of 3. 4 comma 1, 4 is a multiple of 1, 4 comma 2 I can write because 4 is a multiple of 2. It is in such a way that 2 2s is 4. So we can say 4 is a multiple of 2. Next we have 6 comma 1, 6 comma 2. Right? 6 is a multiple of 1. 6 is a multiple of 2 because 2 3s are 6. Then we have 6 comma 3. 6 is a multiple of 3 because 3 2s are 6. And lastly 6 comma 6. So this is how the relation R can be written. Because it was given that A is a multiple of B, we have to choose on the elements of the set A. A consists of the elements 1, 2, 3, 4, 6. Right. Now, this was the first part of the question. Secondly, we have to draw its digraph. So, based on the relation R, let us write down the digraph. Let us now write down the digraph. So, I have 5 elements on the set A. 1, 2, 3, 4, 6. We shall represent each of these elements as the vertices or the circle. Okay, or the circles, and then draw the digraph. So first I'll represent those 1, 2, 3, 4, 6 as circles. You can represent anywhere that you want. So I'll take 1, then 2 here, say 3, 4, 6. So these are our elements of the set A. Elements of the set A. Now we have to draw an edge in such a way that based on the relation R, means from 1 to 1 there is an edge, that is a loop, because you have relation R starting from 1 comma 1. So 1 comma 1 represents 1 to 1, you have to draw a loop. 1 to 1 we have to draw a loop. Then we have 2 comma 1. The next element is 2 comma 1. So 2 to 1 we will draw an edge. 2 to 1. Then 2 comma 2, a loop. 2 comma 2. Then we have 3 comma 1, 3 comma 3. So 3 to 1 I will draw an edge. 3 comma 3, so a loop from 3 to 3. Next we have 4 comma 1, 4 comma 2. 4 to 1 I will draw an edge. 4 to 2 there should be an edge from 4 to 2, 4 to 2, just a minute. Yes, we will represent 4, 1, 4, 2. So 4 to 1 I represent in an edge. 4 to 2 there should be an edge. While writing the relation R, I have missed out 4, 4 because 4 is a multiple of 4 itself. So I have to write down that, which I just wrote. You just observe that. And 4 to 4, we will draw a loop. Then we have 6, 1. So 6 to 1, I should draw an edge. Then 6 to 2, there should be an edge. 6 to 2, there should be an edge. 6 to 3. 6 to 3, there should be an edge. Then lastly, 6 to 6, a loop. So this is how a digraph can be written. Digraph of a relation R. So this is the digraph of relation R, which is nothing but the second part of the sub-question. Thirdly, determine the in degrees and out degrees of the vertices. Let us represent this in the form of a table, small table. Okay, I will write down the vertices here, and it's in degree and out degree. So which are the vertices that we have? We have vertex 1, 2, 3, 4 and 6. Let us write down the in degrees for all these vertices. So in degrees means number of vertices coming to that vertex gives us the in degree. This can be written by looking into the digraph. So let us count the in degrees looking into the digraph coming to the vertex 1. In degree of 1 we are finding. So coming to the vertex 1. 1, this is one edge coming to it. 3 to 1, 4 to 1, 6 to 1 and 1 to 1. So we have 5 edges coming to the vertex 1. So in degree of 1 is 5. Similarly, in degree of the vertex 2. So loop gives us one count, 6 to 1. We have 4 to 2. So there are 3 edges coming to the vertex 2. So in degree of 2 is 3. Then we need to write down in degree of the vertex 3. So in degree of the vertex 3 is a loop is counted. Then 6 to 3 there is an edge. So in degree of 3 is only 2 edges are coming to the vertex 3. Only 2 edges. So in degree of 3 is 2. Then in degree of 4 loop. Only the loop is counted in degree of 4. So which is 1. And finally in degree of 6 is also 1 because only the loop is counted. So in degree of 6 is 1. Now we will find out the out degrees. So out degrees of each of these vertices 1, 2, 3, 4, 6 has to be found out. Out degree means number of edges going out of that vertex. So out degree of 1 means number of edges going out from 1. So 1 in the how many edges are going? That loop only. Loop only. So out degree of 1 is 1. Out degree of 2. Loop is counted and from 2 to 1 we have an edge. 2 to 1 we have an edge, no? So 2 edges are going away from 2. The loop as well as from 2 to 1. So out degree of 2 is 2. Out degree of 3. 3 to 1. Then we have 3 to 3. So again out degree of 3 is 2. Out degree of 4 is 3. Out degree of 4 is 3 because loop is counted. Then 4, 2 is one of the edge and 4, 1 is another edge. Going from 4. That is why out degree of 4 is 3. Now out degree of 6 is nothing but from 6 we have 6 to 1, 6 to 3, then 6 to 2, 6 to 6. So there are 4 edges going away from 6. So out degree of 6 is 4. Out degree of 6 is 4. Now last subpart of the question, we need to write down the matrix of the relation R. Okay. So let us write down the matrix of the relation R. Fourth subpart of the question, matrix of the relation R. MR, M of R, or it is also represented as M suffix R. Now this should be defined on the relation A on A. Correct? A has 5 elements. 1, 2, 3, 4, 6. So there are 5 elements, means we will get 5 cross 5 matrix. How do we write down the matrix of the relation R? There will be an edge, or if there is an ordered pair 1, 1, then from 1 to 1 there is an edge, means you are going to represent it by 1. There does not exist 1, 2, 1, 3, 1, 4, 1, 6 if you observe. So all that represented as zeros. Let us write down that. So we have a 5 cross 5 matrix. Before we write down that 5 cross 5 matrix, let us first represent the outside numbers as the elements of the set A. 1, 2, 3, 4, 6. 1, 2, 3, 4, 6. We are just representing this outside for our understanding purpose. Now 1, 1. From the relation R, we have 1, 1. So 1 and 1 is associated here. If you observe 1 to this 1, there is a relation. So that's why I have to represent 1 over here. 1, 2, 1, 3, 1, 4, 1, 6 does not exist. So in the same row, all other elements will be 0. So I have 1, 0, 0, 0, 0. Then second row, let us go back to the relation and just see. With 2, we have 2, 1, 2, 2. 2, 1, 2, 2. So 2, 1 is nothing but 2, 1. That is second row, first column. Second row, second column gives us 1. The rest all elements will be 0. So recall the definition for matrix of a relation. There will be an edge AI, AJ. If there is an edge between AI, AJ, then the element in the matrix will be 1. Otherwise, it is 0. So we have 1, 1, 0, 0, 0. Next, starting from 3, we will looking into the relation 3, 1, 3, 3. I have to represent 3, 1, 3, 3. We need to represent. Rest all are 0. So 3, 1 is third row, first column, and then third row, third column is 1. Rest all are zeros. 1, 1. 3, 1, 3, 3. Rest all are zeros. Then we have the fourth, starting from 4, we have 4, 1, 4, 2, 4, 4. 4, 1, 4, 2, 4, 4. So 4, 1 is this element, 4, 2, 4, 4. The rest all are zeros. And finally, starting with 6, we have 6, 1, 6, 2, 6, 3, 6, 6. 6, 1, 6, 2, 6, 1, 6, 2, 6, 3, 6, 6. The element 6, 4 is not existing in the relation R, so 0 here. So this is how the matrix of a relation can be written. Hope you have followed this problem. Let us see the next problem on composition of relations. Third one. Let A be the set given as 1, 2, 3, 4 and R be the relation defined as 1, 1, 1, 2, 2, 3, 3, 4, 3, 4. S be the relation defined as 3, 1, 4, 4, 2, 4, 1, 4. So two relations are defined for us. B. Relations on A. The relations on A determine relations R composition S, S composition R, comma R composition S composition R, S composition R composition S, S composition R, R square and S square. So the entire problem is to find the composition of different relations, right? So let us see solution. Solution. Let us find one by one. So first one is R composition S. R composition S. We'll recall the definition for composition of two relations. So if there is an element A comma B belonging to R, and if there is an element B comma C belongs to S, then A comma C belongs to the composition of the element. So what I mean to say is, we'll consider this relation, the set ordered pair here 1, 1. So if 1, 1 belongs to R, and if there is an element starting with this term 1 here, starting from 1 in the set S, that is 1, 4 I can see here, correct? So 1, 1 exists in R, 1, 4 exists in S. So 1, 4 exists in R composition S. 1, 4 exists in R composition S. So whatever the element ends here, the element should have been started here in the S. I repeat, A comma B belongs to R, B comma C belongs to S, then A comma C belongs to R composition S. That is what is the definition for composition of two relations. So 1, 1 belongs to R, 1, 4 belongs to S. That is why 1, 4 belongs to S, R composition S. Now next element. Starting with 1, there are no more elements. So 1, 1 work is over. 1, 1 work is over. I'll just put a tick here for understanding purpose. 1, 2 element exists in R. Starting with 2, we have 2, 4. This is ending with 2. So we have to search an element starting with 2 to write down. Easy way of understanding this is that's all. So 1, 2 belongs to R. 2, 4 belongs to S. So 1, 4 belongs to R composition S, which you have already written. So we will not repeat it once again. Now there is no other element starting with 2 here. So we'll move on to 2. So 1, 2 work is over. Next we have 2, 3. 2, 3 belongs to R. So this is ending with 3. I have to see in the set S starting with 3. It is 3, 1. So 2, 3 belongs to R. 3, 1 belongs to S. So 2, 1 belongs to R composition S. 2, 1 belongs to R composition S. AB belongs to R, BC belongs to S. So AC belongs to R composition S. So there is no other element starting with 3 here. So 2, 3 work is over. Then the last element is 3, 4. 3, 4. This is ending with 4. So I have to look into an element starting with 4 in the set S. So this is 4, 4 here, starting with 4. So 3, 4 belongs to R. 4, 4 belongs to S. So 3, 4 belongs to A, C belongs to R composition S. So 3, 4. So these are the compositions that exist for our composition S. So 3, 4 work is also over. So this was R composition S for us. Now let us see S composition R. S composition R. So first you have to look into the relation S and then followed by relation R. S composition R we want to know, that's why. So 3, 1 belongs to S. Starting with 1 we have 1, 1, 1, 2. So 3, 1 belongs to S composition R and 3, 2 belongs to S composition R. 3, 1, 3, 2. 3, 1, 3, 2. I repeat that once again for your understanding. 3, 1 belongs to S. You have to look S composition R, no? So 3, 1, this is ending with 1. So I have to look in the relation R starting with 1. This is 1, 1, 1, 2. Now A, C you have to collect. A is nothing but 3. C is nothing but the ending element here. It is 1. Here it is 2. 3, 1, 3, 2 are the elements. So 3, 1 work is over. I'll just put a tick for your reference. Now starting with 4. 4, 4 is an element here. So start ending with 4 here. Starting with 4, there are no elements here. There are no elements here. So 4, 4, there is nothing to do with it. This work is over. 2, 4 here again ending with 4. There is no element starting with 4 here. 1, 4, this is ending with 4. There is no element starting with 4 again. That is why I have closed the set here. S composition R is only with these two elements. So this was R composition S composition R for us, which we completed. Now we'll move on to R composition S composition R. R composition S composition R. So sometimes what happens, for convenient, we can write down these relations also for our understanding. That is, R is nothing but, I'll write down the relation R once again. 1, 1, 1, 2, 2, 3, 3, 4. This is relation R for us. Composition. S composition R we will write down. S composition R we will write down. S composition R just now we found it as 3, 1, 3, 2. 3, 1, 3, 2. So we will have to do composition of these two elements. So S composition R is nothing but 3, 1, 3, 2. Okay, we will do composition of these sets. Right. Now look at this expression 1, 1. This is ending with 1. There is no element starting with 1 here. So with 1, 1, I cannot get any compositions. So 1, 1 work is over. 1, 2. This is ending with 2. There is no element starting with 2 here. So that is why there is no compositions starting with 1, 2. There is no compositions. Then we have 2, 3. This is ending with 3 and these are the elements starting with 3 here. So we can write down 2, 3, 3, 1 gives us 2, 1. 2, 1. Next, 2, 3, 3, 2 gives us 2, 2. 2, 2. So with 2, 3, both I can match and write down the composition. Correct? So 2, 3 work is over. 2, 3 work is over. Next we have, which one I have to find out now? With 3, 4. 3, 4 means this is ending with 4. There is no elements in the expression here starting with 4. So 3, 4 composition, nothing will happen. So that is why 3, 4 work is over. So this is R composition, S composition R for us. R composition, S composition R for us. This was our third subpart of the question which we did just now. Correct? Now we will move on to the next one. The fourth one that we have to find out is S composition R composition S. S composition R composition S. We'll write on that S composition R composition S. First we will write down the relation S. Relation S consists of 3, 1, 4, 4, 2, 4, 1, 4. Composition R composition S. R composition S has the elements 1, 4, 2, 1, 3, 4. 3, 4. Okay. So this is equal to, now we will select all those elements. We'll do one by one. 3, 1. This is ending with 1. This is 1, 4. So 3, 1, 1, 4 gives us 3, 4. 3, 1, 1, 4. 3, 1, 1, 4 gives us 3, 4. 3, 1 work is over because there is no other element starting with 1. So 3, 4, 3, 1 work is over. Next 4, 4. This is ending with 4. There are no elements starting with 4 here. So with 4, 4 I cannot make any other composition. So 4, 4 work is over. Similarly this is 2, 4. Ending with 4. There is no element starting with 4. 1, 4. This is no element starting with 4. So 2, 4, 1, 4 work is also over. So this is the only set that is consisting in S composition, R composition S. This was the fourth sub question for us. Next we have to find S composition R. S composition R. We'll write down the set S first for convenient. So we have 3, 1, 4, 4, 2, 4, 1, 4. Composition S composition R. S composition R we have just found out 3, 1, 3, 2. So I will write down that 3, 1, 3, 2. Now we will do composition of these two sets. 3, 1. This is ending with 1. There is no element starting with 1 here. So 3, 1 work is over. Next we have 4, 4. Ending with 4. There is no element starting with 4 in the second set here. So 4, 4 work is over. Then we have 2, 4. Ending with 4. There is no element starting with 4. So 2, 4 work is also over. Then 1, 4 is ending with 4. Here starting with 4 there are no elements. So 1, 4 work is also over. So we did not get any elements in this set. Which is one and the same as telling it's a null set. It is a null set. The next we will find out R square. R square. R square is nothing but R composition R. R composition R. From the definition, R square is nothing but R composition R. Let us write down those R elements here for convenient. R is given by 1, 1, 1, 2, 2, 3, 3, 4. I have to do composition of same set once again. That is 1, 1, 1, 2, 2, 3, 3, 4. 2, 3, 3, 4. Let us do our composition as R composition R, which is nothing but R square. So if you observe, this is 1, 1. I have to search 1, 1. This is ending with 1. This is starting with 1. So 1, 1, 1, 1 gives us back 1, 1 itself. Then I have 1, 1, 1, 2. 1, 1, 1, 2 gives me 1, 2. Then I have 1, 1 and no other element is starting with 1. So this 1, 1 work in the first part is over. Next we have 1, 2. Ending with 2, I have to search for starting with 2. Starting with 2, this is the element. So 1, 2, 2, 3 gives us 1, 3. 1, 2, 2, 3 gives us 1, 3. That was the only element starting with 2. So 1, 2 work is over. Next 2, 3. This is ending with 3. Starting with 3, I have 3, 4. So 2, 3, 3, 4 gives us 2, 4. 2, 4. 2, 4. So if you observe, those are the only elements we have, because 2, 3, 3, 4, we have ending with 3, here starting with 3. So 2, 3, 3, 4 gives us 2, 4, and 2, 3 work is over. This is an element 3, 4. There is no element starting with 4 here. So 3, 4 work is over. This is R square for us. I leave it to the students to do S square. So how do you do S square? S square is obtained by S composition S. S composition S. You can try that doing for yourself. I'll just reveal the answer. S composition S should be the set of ordered pairs 3, 4, 4, 4, 2, 4, 1, 4. I repeat, 3, 4, 4, 4, 2, 4, 1, 4. Hope you understood this problem. Let us see next problem. Fourth one. Let A be the set 1, 2, 3, 4. B be another set W, X, Y, Z. And C be the third set given for us 5, 6, 7. Let R1 be the relation from A to B, R2 be the relation from B to C, and R3 also be the relation from B to C, defined by R1 is equal to 1, x, 2, x, 3y, 3z, and R2 be the relation defined as W5, X6, R3 be the relation defined as W5, W6. Then find first sub question R1 composition R2 and R1 composition R3. Second sub question, find matrix of R1, matrix R2 and matrix R1 composition R2. The third subquad of the question is verify matrix R1 composition R2 is equal to matrix R1 into matrix R2. So sets A, B, C are given for us. R1, R2, R3 are defined, which are given as below. We need to find composition of two functions, two relations R1, R2 and R1, R3. Then we have to find out matrix R1, matrix R2 and matrix R1 composition R2. And we need to finally verify matrix of R1 composition R2 is equal to matrix R1 into matrix R2. So let us do the solution for the same. Solution. We have to find out R1 composition R2. So first sub question is to find R1 composition R2. So we will write down what is R1. 1x, 2x, 3y, 3z. Composition R2 is W5, X6. W5, X6. So we will start with one by one. This is 1x. Here we have x6. Composition of two relations we are trying to do. So 1x, composition x6. A comma B belongs to R1. B comma C belongs to R2. Then A comma C belongs to R1 composition R2. That's a basic definition for composition of two relations. So 1x, this is ending with x. So we look into starting with x element in the next set. So 1x, x6 gives us 1 comma 6. 1 comma 6. That's the only element starting with 6 here. So 1 comma x work is over. Next 2 comma x. This is x comma 6. So 2x, x6 gives us 2 comma 6. 2 comma 6. So 2x work is over. This is 3y. There's no element starting with y here. So 3y work is over because we are not getting any element along with or starting with y in the second set. So 3y work is over. Next we have 3z composition W5x6. So there's no element starting with z here. So 3z work is also over. So we have R1 composition R2 is equal to 1 comma 6 and 2 comma 6. And in the same sub question we also have to find out R1 composition R3. R1 composition R3. So this is given by R1 composition R3 we have asked to find. We will write down R1 first. 1 comma x, 2 comma x, 3 comma y, 3 comma z. Composition R3. R3 is given by W5, W6. W5, W6. So this is the element. We have 1 comma x. There is no element starting with x. So nothing to do with 1 comma x. Then we have 2 comma x. Again this is ending with x. There is no element in the second set starting with x. So this work is also over. 3y. 3y. So this is ending with y. There is no element starting with y here. So 3y work is all over. 3z. There is no element starting with z here. So 3z work is also over. So we did not get any elements in the composition of R1 and R3, which is same as telling this is a null set. This is a null set. R1 composition R3 is a null set. So this was our first sub part of the problem. Now we will move on to second part of the question. Second sub part of the question. Find matrix of R1, matrix of R2 and matrix R1 composition R2. So I have to find one by one matrices. Looking into R1, matrix R1 I have to find out. R1 has the elements 1x, 2x, 3y, 3z. And R1 is a relation from A to B. So you should write down A elements across rows and B elements across column. So A has 4 elements, B has 4 elements. So resultant matrix, that is matrix of R1 will be a 4 cross 4 matrix. So let us represent that now. So we'll find matrix R1 now. Matrix R1. Matrix R1. So this is given by, first we will have to write down the elements of R1 across row. That is we have 1, 2, 3, 4. And the elements of B across R1 is a relation from A to B. Correct? So that is why elements of B across columns. So W, X, Y, Z. Across columns W, X, Y, Z. So this will, the resultant matrix will be a 4 cross 4 matrix. 4 cross 4 matrix. So let us represent this matrix now. So R1 is defined as 1 comma x, 2 comma x, 3y, 3z. So we have 1x. X is here. So first row, second column, there will be an element 1. 1. Then we have 2x. So second row, second column, 2x, second row, second column. So there will be 1 here. And third element is 3 comma y, 3 comma y. Third row, third column will be 1. And finally 3 comma z. So 3 comma z will be third row, fourth column. Right? There are only 4 ordered pairs in R1. So I have 4 ones. The rest all will be zeros in the matrix. So let us fill zeros. Zeros. So this is matrix R1. Similarly, we have to write down matrix R2. Matrix of R2. So M of R2 is equal to, R2 is a relation from B to C. R2 is a relation from B to C. So B has the elements W, X, Y, Z, which will represent across row, and C. C has 3 elements, 5, 6, 7. This we need to represent column wise. So W, X, Y, Z across row, W, X, Y, Z across row, and across column the elements of set C. So 5, 6, 7. 5, 6, 7. So the resultant matrix will be a 4 cross 3 matrix. 4 cross 3 matrix. So let us represent the elements here. So how is R2 given by? R2 is a relation defined as W comma 5, X comma 6. So W5, first row, first column will be 1. Then we have X comma 6. So second row, second column. Second row, second column will be 1. The rest all elements will be 0 because there are no more elements in the relation R2 defined. So in relation R2, there are no more elements. So rest all elements will be 0. Right? So this is how we find out matrix of R2. Now finally, in the second sub question, we also have to find matrix R1 composition R2. Matrix R1 composition R2. Let us find that. Matrix of R1 composition R2. R1 composition R2 we have found out in the first sub question, which is 1, 6 and 2, 6. Right? And R1 composition R2 is a relation. It is which relation? We have to recognize that first. Matrix R1 composition R2 we have to find out. R1 composition R2. So R1 is a relation from A to B. R2 is a relation from B to C. So the resultant matrix, the resultant will be a relation from A to C. I repeat, R1 is a relation. R1 is a relation from A to B. R2 is a relation from B to C. So the resultant will be R1 composition R2, which will be a relation from A to C. So across row, we have to write down the elements of A. Across columns, we have to write down the elements of C. Okay, first we will represent elements of A across row, that is 1, 2, 3, 4. 1, 2, 3, 4. And across column, we will write down the elements of C. Elements of C are 5, 6, 7. So here also resultant matrix will be a 4 cross 3. 4 cross 3 matrix. So let us write down R1 composition R2 has elements 1, 6, 2, 6. So 1, 6 is first row, second column. 2, 6 is second row, second column. First row, first column will be 1. Second row, second column will be 1. So in R1 composition R2, there are only 2 elements, 1, 6 and 2, 6. So we have filled those by ones. Rest all elements will be zeros in the matrix. So rest all elements are zeros. Right? So this is how we find out matrix R1, matrix R2 and matrix R1 composition R2. Now the third part and the last part of the question is to verify matrix R1 composition R2 is equal to matrix R1 into matrix R2. Right? To find out this, we have already found out matrix R1 composition R2 here. So we are not finding it once again. We just have to do the product of the matrices. This is general product of any two matrices. Matrix R1 we have found out, matrix R2 we have found out. We need to do the multiplication, normal multiplication of matrices. So when we do that, the resultant should be equal to matrix R1 composition R2. So let us check whether it is so or not. Okay. So I will take up, consider for the third sub part of the problem, consider matrix R1 into matrix R2. Matrix R1 into matrix R2. So matrix R1 we have found out in the previous page. I'll just go there. Matrix R1 is 0 1 0 0 0 1 0 0 double 0 double 1 and all zeros. I'll just write on the same thing. 0 1 0 0 0 1 0 0. Third row is 0 0 1 1. Fourth row is all zeros. Multiplied by, we have matrix R2 given by 1 0 0 0 1 0 0 0 0 0 0 0. We'll write down that matrix 1 0 0 0 1 0 0 0 0 and last row also 0 0 0. 4 cross 4 matrix multiplied by 4 cross 3. So resultant matrix will be a 4 cross 3 matrix. Let us obtain by doing the product of the matrices. All of you are familiar with product of two matrices, no? So every row is being multiplied by the column of the second matrix. Correct? This is how we perform the product of two matrices. So 0 into 1 plus 1 into 0 plus 0 into 0 plus 0 into 0. That is how we perform, which gives us the resultant as 0. Again, 0 into 0, second column we are multiplying with the first row here. So 0 into 0 plus 1 into 1 plus 0 into 0 plus 0 into 0. So resultant matrix is 1, element is 1. Next, first row with the third column. Since all are zeros here, the resultant will be, product will be 0. Then again we have 0, 1, 0, 0 multiplied with the first column here. Second row with the first column, resultant is 0. Second row with the second column. So 0 into 0 plus 1 into this 1 and 0 into 0, 0 into 0. So 1 into 1 is multiplied. That's why 1 here. And the second row with the third column, all are zeros. So resultant will be 0. Then third row with the first column will be 0. Third row with the second column will also be 0. Third row with the third column will be 0. You can just check that for the remaining elements. All will be equal to 0. So this is our resultant matrix. Let us check whether this is equal to matrix of R1 composition R2. Yes, it is also the same thing. So we can just conclude this is equal to matrix R1 composition R2. So therefore, we can conclude matrix R1 composition R2 is equal to matrix R1 into matrix R2. That's all is the solution for this problem. Right. Let us see the next problem, fifth one. Suppose set A is given for us, A equal to 1, 2, 3, 4 and R is a relation, R is a relation on A defined by R is equal to 1, 2, 1, 3, 2, 4, 3, 2, 3, 3, 3, 4. Find R square and R cube Find r square and r cube. Write down their digraphs. Write down their digraphs. Find matrix of R, matrix R square, matrix R cube, and hence verify that matrix R square is equal to matrix R whole square, and matrix R cube is equal to matrix of R the whole cube. So these are the two things that we have to prove. So let us see the solution part. Solution. So firstly we have to find R square. R square, which is R composition R. R composition R. So R on R itself. So I'll just write down the elements for convenient. 1, 2, 1, 3, 2, 4, 3, 2, 3, 3, 3, 4. Composition, the same elements. 1, 2, 1, 3, 2, 4, 3, 2, 3, 3, 3, 4. So R square will be composition of these elements. So 1, 2, this is ending with 2, starting with 2 we have 2, 4. So 1, 2, 2, 4 gives us 1, 4. Then there are no elements starting with 2 here. So 1, 2 work is over. 1, 3, 3, 2 gives 1, 2, 1, 2. Then again 1, 3 composition. 3, 3 gives us 1, 3. Then 1, 3 composition 3, 4 gives us 1, 4, which is already written. So 1, 3 work is over. 2, 4. There is no element starting with 4 here. So 2, 4 work is over. 3, 2 composition 2, 4. 3, 2 composition 2, 4 gives us 3, 4. Gives us 3, 4. Then we have 3, 2. This is no more elements starting with 2. So 3, 2 work is over. Then we have 3, 3 composition 3, 2, which gives 3, 2. And we have 3, 3 composition 3, 3, which gives 3, 3 for us. Then 3, 3 composition 3, 4 gives us 3, 4, which is already written here. So 3, 3 work is over. Next we have 3, 4, and there are no elements starting with 4. So we have this as our answer for R square. R square, which is nothing but R composition R. R composition R. Right. Now let us find R cube. The next that we have to find out is R cube. So R cube is nothing but R square composition R. This we can also take it as R composition R square. Both are correct. We'll fetch you the same answer. So we have R square composition R to do with. I'll just write down R square what we obtained just now. 1, 4, 1, 2, 1, 3, 3, 4, 3, 2, 3, 3. Composition R. The relation R is given by 1, 2, 1, 3, 2, 4, 3, 2, 3, 3, 3, 4. So performing the composition of these two relations, we obtain 1 4 composition. I have to search for elements starting with 4. Uh, there is no ordered pair starting with 4. So 1 4 work is done. 1 2 2 4. So this is an element 1 2 composition 2 4. So gives us 1 comma 4. So I'll write down 1 comma 4. 1 2 work is over. Similarly 1 3 composition 3 2 will gives us 1 2, and 1 3 composition 3 3 gives us 1 3. 1 3 composition 3 4 gives us 1 4, which is already written, so we will not repeat it. So 1 3 work is over. 3 4, there's no element starting with 4 in the second relation, so 3 4 work is done. Then we have 3 2 2 4 gives us 3 4. 3 2, there's no other element starting with 2, so 3 2 work is over. Then we have 3 3 3 2, which gives 3 2. 3 3 3 2 gives us 3 2. 3 3 3 3 gives us 3 3. And finally 3 3 3 4 gives us 3 4, which is already written here. So we will not repeat it. Just a small observation that r square and r cube values are equal. Whatever you obtained the r square, that is r composition r, is same as the answer for r cube, what you obtained just now. Okay, that's just an observation for your reference. Now we have to find out the next part of the problem is to write down their digraphs. Write down their digraphs means we have to write down the digraph of r square and r cube. So r square and r cube digraphs are same. So I'll just, since r square, r cube are same, the digraphs of r square and r cube will be same. So I'll just write down the digraphs for you. Digraphs of r square and r cube are same as shown below. So let us write down the digraphs of r square and r cube. So looking into r square and r cube, r square is nothing but r composition r, means a on a. R composition r is a on a. So we will get 4, we have 4 elements 1 2 3 4 to write down the graphs for us. So let us represent 1 2 3 4. The order of or the way of writing these circles or the vertices is left to the writer's choice. Okay, so r square and r cube has the same digraphs. The elements are 1 4 1 2 1 3, 1 4 1 2 1 3, 1 4 1 2 1 3. Then the next set of elements are 3 4 3 2 3 3, 3 4 3 2 3 3. 3 to 3, so there is a loop. Okay, so this is digraph of r square or same as digraph of r cube, right? Digraph of r square as well as of r cube. So the next part, second part of the problem that we have to find. Finally, we have to find out matrix of r, matrix of r square, matrix of r cube, and we have to verify along with this properties. Okay, so let us find matrix r square, matrix r cube. Matrix r. Matrix of r is a relation r on r, a on a. So a has how many elements? The set A has 4 elements. So 4 cross 4 matrix, 1 2 3 4, 1 2 3 4. So let us represent that 1 2 3 4, and across column also 1 2 3 4. matrix of R we are writing. So R has the elements, R has the set 1, 2, 1, 3, 2, 4, 3, 2, 3, 3, 3, 4. So we have to represent all these. 1, 2, 1, 3 we will represent first. 1, 2. First row, second column will be 1. 1, 3. First row, third column will be 1. Next, we are looking into relation R, no? 2, 4, 3, 2. 2, 4 will be second row, fourth column will be 1. Then 3, 2. Third row, second column will be 1. We also have in the relation R 3, 3, 3, 4. 3, 3, 3, 4 will be third row, third column, third row, fourth column. So we have how many ones? 3 plus 3, 6 ones. And there should be 6 ordered pairs in the relation R. True, no? So rest all elements in the matrix will be 0. Rest all elements in the matrix are zeros. So this was matrix R for us. Now matrix R square will be same as matrix R cube, no? Because R square and R cube are equal, matrix of R square will be same as matrix of R cube. We will represent that. So matrix R equal to matrix R square, which is given by, again this is a relation R on R, defined A on A. So we have 1, 2, 3, 4 across rows, as well as 1, 2, 3, 4 across columns. So let us represent this relation looking into R square or R cube. Any one of them we can look into since both are equal. 1, 4, 1, 2, 1, 3. 1, 4, 1, 2, 1, 3. Next we have 3, 4, 3, 2, 3, 3. 3, 4, 3, 2, 3, 3. These are the 6 ordered pairs existing in R square or R cube. I should have written here matrix R square, which is equal to matrix R cube. Correct? So this should have been square and this is cube for us. Cube. Okay? Now it's fine, I believe. So rest all elements in the matrix are zeros. Rest all elements in the matrix are 0. So this is matrix R square, which is matrix R cube for us. Now we will do matrix of product of two matrices. The next part of the problem is to verify matrix R square is equal to matrix R the whole square. Matrix R square just now we obtained. This is our matrix R square. We have to verify whether this is equal to matrix R the whole square. Means matrix R into matrix R is nothing but matrix R the whole square. So let us do product of matrix R into matrix R. So matrix R square will be equal to matrix R into matrix R, which is equal to R. Matrix R is this matrix for us, 0, 1, 1, 0. Second row is 0, 0, 1, 0, 1, 1, 1. Finally, all zeros multiplied with same matrix 0, 1, 1, 0, 0, 0, 0, 1, 0, 1, 1, 1 and all zeros. Again the same concept, every row should be multiplied by the column in the second matrix. Usual matrix multiplication. Right? Resultant will also be a 4 cross 4 matrix because both these are 4 cross 4 matrices. So let us do the matrix product. First row is multiplied with the first column. All are zeros. So resultant matrix will be all zeros. No. First row with the first column. So 0 into 0 will be 0. 0, 1 into 0 will be 0. 1 into 0 is 0. 0 into 0 is 0. So first element is 0. Then again first row with the second column. First row with the second column will give us 0 into 1 is 0. 1 into 0 is 0. 1 into 1 is 1. 0 into 0 is 0. So sum will be 1. First row with the third column, 0 into 1 is 0, 1 into 0 is 0, 1 into 1 is 1, 0 into 0 is 0. So the sum is 1, I believe. The next value, 0 into 0 is 0, 1 into 1 is 1. Again we have 1 into 1 is 1. Last one, 0 into 0. So did you observe that we have two sum of ones? 1 plus 1 we are getting no. 1 into this 1 is 1 and 1 into 1 is 1. When you add them, the sum is actually 2. But recall the definition of matrix relation. It is full of zeros and ones only. So we stipulate and we write down here 1 plus 1 is 1 itself, since the matrix of a relation should have only zeros and ones. Should have only zeros and ones. So this sum will still remain to be 1 itself. Okay. Similarly, we continue doing the product. Second row with the every column, third row with all the columns, fourth row with all the columns. I'll directly write down the result into you. You can just do the matrix multiplication and verify. So is this equal to matrix of R square? Check out matrix of R square that we had obtained. So this matrix R into matrix R should be equal to matrix of R square, what we had already obtained. Right? It is equal to. So what we have done here is we have stipulated 1 plus 1 is equal to 1 itself. We have stipulated this since matrix of a relation should contain zeros and ones only. Zeros and ones only. Right? So this is another important problem. I leave to the students to work out. Matrix R cube is equal to matrix R the whole cube. Matrix R the whole cube. So I have just left this for the students to do. I would like to take up one last problem for your reference, which is based on the converse. And we'll find out as well there the union and the intersection of two relations. These were the operations on relations that we dealt now. In the theory we had looked into. So I would like to just take up one last problem based on the same thing. Okay. So if I'm not wrong, this is problem number 6 for us. The digraphs of two relations R and S on the set A equal to are given below. Write down the question. The digraphs of two relations R and S on the set A equal to A, B, C are given below. So digraphs are given for us. Draw the digraphs of R complement, R union S, R intersection S, and R converse. R converse. So let us do one by one. So firstly, before I could go to the solution, we are also given with the digraphs for us, right? So in the question part itself, the digraphs is given for us. So we will first write down the digraph. Okay. So let us see what is the digraph given. R is given for us. R is given, which is A, B, C. There's a loop from A to A, an edge from A to B, B to C, A to C is given for us. Then the relation S is represented in the form of a digraph. A, B, C. Both these relations are from A on A itself. So there is an edge from B to A, B to C, A to C, and C on C itself. C on C. So this is digraph for the relations R and S given for us. So what are we asked to find out? We are asked to find out or draw the digraphs of R complement, R union S, R intersection S, and R converse. First we need to find all of them and then we'll have to draw the digraphs. It's an easy one. Let's do the solution. So from the digraphs, we should be able to recognize how is the relation R given by and how is the relation S given by. So R is the relation from the digraph I can recognize. There is a loop from A to A. So A comma A. There is an edge from A to B. Correct? Observe the arrow. There is an edge from A to B. So A comma B. There is an edge from B to C. So B comma C. The order does not matter. A to C there is an edge. So A comma C. So there are 4 elements. You can observe there are 4 edges in the digraph here. Loop represents one edge. So there are totally 4 edges. This is how the relation R is written looking into the digraph. Now we have S. S is given by B comma A, B comma A comma C, B, C, C, C. There are again 4 edges including the loop. So we have written all those in the form of the ordered pairs. Arrows are important. They represent the ordered pair here. Now looking into R and S, we have to write down R complement. R complement. R complement is a set of all those ordered pairs which are there in A cross B but not in R. So I have to write down. So since A comma A, we have the ordered pairs observing here. A comma A R complement we are representing. So A comma A, B and AC are existing. So all pairs AA, AB, AC are existing. So with A, there is no complement. Observe with B, BC is existing. So what is not there in the set of all ordered pairs A cross A? So BC is the only ordered pair existing here. B comma A is missing. BB is missing. So we will write down that here. BA, BB. So R complement is a set of all those elements taken from A cross B minus R. A cross B is a set of all ordered pairs from A on B. Here we are defining A on A itself. Okay. Then we have looking into R. Starting with C, there are no elements at all. So I have to write down all the elements starting with C. That is CA, CB, CC. CA, CB, CC. So this is R complement for us. Next we will write down R union S. Looking into the union. AA, AB, BA, AC, BC, then CC. So these are the elements of R union S. AA, AB. It's a usual union of 2 sets for us. AC, BA, BC, CC. So this is R union S. Now R intersection S. R intersection S is given by common elements in the set R and set S. Okay, so we observe AC is common and we observe B comma C is common. So A comma C and B comma C. Finally, R converse. Let us recall the definition for R converse or converse of a relation. It says that any element A comma B, if it belongs to the relation R, then B comma A belongs to its converse. So we have A comma A belonging to R. So the reverse of these elements will be A comma A itself. So A comma A belongs to R converse. If A comma B belongs to R, then B comma A belongs to R converse. If B comma C belongs to R, then C comma B, CB belongs to R converse. If AC belongs to R, then CA belongs to R converse. So the reverse of the elements will be written in the converse of relation. Okay? So these are our relations that we had to obtain. Now the question is to draw the digraphs of all these. So let us quickly draw the digraphs of all these. Digraphs. So first one for R complement I am writing A, B, C. R complement has the ordered pairs BA, BB, BA, BB, then CA, CB, CC. CA, CB, CC. This is for R complement. Next we have R union S. R union S. Again the elements are A, B, C. R union S has the elements AA, AB, AC, AA, AB, AC, BA, BC, CC. BA, BA. So I can just put an arrow like this. Then BC, CC loop. This is for R union S. Then for R intersection S, let us write down the elements A, B, C. Intersection, we are representing R intersection has the elements AC, BC. So AC, BC. This is the diagram for R intersection S. Finally, for R converse. R converse, first we will represent A, B, C as the vertices or the nodes. We have elements AA, BA, AA, BA, and then we have CB, CA, CB, CA. So these are the diagrams of all the four required things. Hope all these problems have been followed to all of you. I'll just give some practice questions so that you can practice these questions, which will help you to understand and have a better clarity. Practice questions. For the set A equal to 1, 2, 3, 4 and let R and S be the relations on A defined by R equal to 1, 2, 1, 3, 2, 4, 4, 4, and S be defined as 1, 1, 1, 2, 1, 3, 1, 4, 2, 3, 2, 4. Find R composition S composition R square, S square, and write the matrices and digraphs of the same. Another question, let R be equal to 1, 1, 1, 2, 2, 3, 3, 3, 3, 4, be a relation on A, which is given by 1, 2, 3, 4. First sub question, draw the digraph of R. Second one, obtain R square, R cube, and draw their digraphs. Third and the last part of the question, find matrix of R square, matrix of R cube. So hope these practice questions will help you to have a better clarity on the topic. Thank you. Thank you very much for watching.